Okay, this is a screenshot from ZenMap, and the screenshot shows scanning results for basic scan types of -ST, -VMAP, or -VNMAP for IP address 192.168.168.5. Now you can see the port status, whether open or closed, as well as what kind of service. This example shows verbose output from Nmap doing a half-open scan of ports 135 through 139 and 443. Now, Nmap by default pings the target host before doing a port scan. You can disable this by using the -P0. Notice that the ports are filtered ports, which means that a firewall is blocking the responses.
A half-open scan, stealth scan, allows the results of a full TCP connect scan without the likelihood of being noted in the destination server's error logs. A frame is sent to TCP port without any handshake or additional packet transfer. What does this mean? The half-open scan partially opens a connection but stops halfway through. The stealth scan sends only SYN packets, so people often call this a SYN scan. This stops the service from ever being notified of the incoming connection.
Now, simple IDS systems may not spot a half-open scan. Firewalls, such as stateful packet inspection firewalls, keep track of the state of each TCP connection, and IDS systems are specifically looking for them. More in-depth monitoring requires higher CPS utilization, and it is used more on business networks than in small offices or homes.
We then have a question.
Yes.
Will stealth scan be able to implement a three-way handshake? And the answer is yes. It can, but it does it differently. Packets that enter the target interface are examined and thereby the remote ports. Before a new installation is triggered, the connection will be determined.
That's right, Laura. And as before, SYN or stealth scanning sends SYN packets to scan the ports and looks at the responses received. And you can include or conclude that the port is open if an acknowledgement to the SYN packet is received by the scanner. The target will try to open a TCP connection. At this stage, the scanner sends a reset flag to tear down the connection. Now, it'll do this before a connection has been fully established. This potentially prevents the connection attempt from appearing in application logs. An RST will be sent if the port is closed, and you'll not get a response if the SYN packet has been dropped. The dropping of a packet happens if the port has been filtered, and we have seen how we can identify if a port has been in open state, closed state, or has been filtered. Now, we'll have to scan further if we can still access some IPs, as filtered ports may apply certain firewall rules. Now, they could be open to some IPs and closed to some.
So let's now look at a ping scan.
Okay.
You can choose a range of IP addresses to scan. The scanner lists the hosts that the hosts that responded to the ping. You can even detect which computers are connected.
Mm-hmm.
And there are 4 methods you can use. We'll start with UDP scanning.
Sounds good.
And UDP scanning has very limited uses for us, but those uses are very important as it can only give details of services such as Trojans that rely on UDP.
Correct.
You should be able to get info about the SNMP, NFS, the back office Trojan backdoor, and such other exploitable services.
Mm-hmm.
Now, most modern services utilize TCP to gather information before an attack or a test. UDP scans will be used only if there is a specific recommendation based on TCP scans or other sources.
That's right. So let's look at the FIN scan. Now, it sends a packet with only the FIN flag set. Null scan sends a packet with no flags switched on. All these scans work on targets that have the TCP and IP information standards. Microsoft does not allow follow RFX, so Windows will ignore data packets from above. Now, that's how you potentially know that you're trying to scan a Windows-based system. If a SYN scan shows an open port and none of the fin and null or Xmas tree shows it is opened, you must be scanning a Windows-based system, right? OS fingerprinting is a reliable way to determine which OS is running on a target. Now, we'll go ahead and go over this a little bit later in the course.
Yeah, now let's go over firewalls. You are aware that we have both stateless and stateful firewalls. So let's see how TCP/ACK works in each case. And we'll also go over what works best in each one or each case. In a TCP/ACK scan, an ACK packet is sent to the target port. An RST reply packet will be sent back in case of an unfiltered port. You may not get a response, or you may get an ICMP destination unreachable response in the case of a filter port. Now you can get through stateless firewalls as they allow ACK packets but block SYN packets. They allow it so that internal hosts can communicate with the internet.
So here's a question. What happens when no response is received? What does that indicate? Now, either the destination server does not exist and it's not powered on to respond to the request, or the port has been firewalled, right? So let's continue by looking at stateful packet inspection firewalls. Now, these work by building a table of open connections to each host. They open a connection only with the completion of the three-way handshake. To check whether a host exists, Nmap will ping the host first. Now, even this can be blocked by the firewalls and scan, and really they can be given away that you are examining a host. To disable this option, use the -PN switch in Nmap. A service detection scan will attempt to communicate with filtered ports to see if they respond to legitimate traffic. Nmap has a range of features to attempt bypassing of firewalls, although knowledge of the defenses you're facing is really still very critical.
Yes, and let's go over how to find out what software and what version is running on a host. This helps us to identify avenues for attack better. Now, Nmap provides a facility with its version detection scan. It will attempt to elicit a response from the ports, which it can then pattern match against its service database. Some of these attempts may be a resource and time intensive. This could be probing a suspect RPC port, which involves flooding it with SYN RPC null commands to see how it responds or what a response is generated. Now, to help alleviate the problems that this can cause, the likelihood of each probe being useful in identifying the service is ranked from 0 to 9. Now, using the version intensified switch in Nmap will allow you to balance the levels of impact you have against the increased chance of identifying a service. Nmap version scan provides reports about ports that are open and services being used, and Nmap also details what is really running. Nmap connects to open ports and probes them further to gather requisite information.
That's right, very good. Now let's look at what additional features Nmap version detection provides. So we have Nmap scans very fast. This is facilitated by parallel operations non-blocking sockets and a probe and match definition grammar. Nmap can identify the application name and version number if they are available. TCP and UDP are supported by Nmap. Nmap supports multiple platforms including Linux, Windows, Mac OS X, FreeBSD, and NetBSD, and OpenBSD. Also, Nmap connects using OpenSSL. If SSL is detected, then it tries to determine the service that is listening behind the encryption layer. This feature enables us to discover services like HTTPS, POPS3S, IMAPS, etc. Nmap launches brute force RPC grinder to find the program number, name, and version number if a SYNRP service is discovered. It supports IP version 6, including TCP, UDP, and SSL over TCP. Nmap prints service fingerprints if it gets data from a service that it does not recognize. That's a really good feature. Nmap has a comprehensive database of various service signatures. Really, it can recognize more than 1,000 service signatures, including more than 180 unique service protocols.